Hi, this is Mark Schuyler. Today we're going to look at cubes, cubes, and cubes. Cubes cubed. Um, the SAT asks a range of questions about cubes. Some of them are quite easy, and we are going to look at a few of the easier things that you need to know about cubes, but we're going to also spend some time at the end on the hardest thing that you would need to know about cubes. So, starting with the easy stuff. You definitely need to know how many faces there are with every single cube. That seems pretty easy, right? Faces. That's easy to know because we often use dice, and the singular of dice is die. There are 6 faces on every die. We also need to know how many vertices there are with every single cube, and vertices are places where lines come together, and we can see that there are 4 vertices here on the top, and there are also 4 vertices on the bottom, and this will make up a total of 8 vertices in all. And then you also need to know the number of edges that every single cube has, and you can see that the 4 edges here on the top of the cube, and then there are also the 4 edges along the bottom of the cube, and the 4 pillars that connect them. So that's 4 plus 4 plus 4, total of 12 edges. And don't confuse the numbers. A lot of people know the numbers are different, but they'll set you up with trap answers where they'll have, say, 8 edges and 12 vertices. Don't get confused. Pretty straightforward stuff. It's also very straightforward to talk about the volume of a cube, how much volume the cube will hold. A cube is a 3-dimensional shape. It's not the 2-dimensional square. And so the volume formula, well, can I just tell you, I have a pet peeve. I can't stand it when students tell me that the volume of a cube is length times width times height. That's really inaccurate. We know that with a cube, every side, every edge is the same length. When you express the volume formula as length times width times height, you're implying that you need 3 different variables because the length is probably different from the height and the width is different. No, we know they're all the same. So really, we shouldn't use that version of what would be a rectangular prism's volume formula. This is a cube, so let's use the side cubed. Much better formula. It's more succinct. It's more concise. It's just plainly more accurate. So remember, side cubed volume formula. The last thing you need to know that's pretty simple is that the surface area is how much wrapping paper you would need to completely wrap up the cube. That's what they're talking about. How much wrapping paper would cover all 6 faces. So what you do to figure out the surface area is you figure out the area of the front face. And we know that that could be expressed as simply the side times the side. So that's side squared. And recalling that there are 6 faces, you have 6 times the side squared. That's the surface area formula for a cube. So not really all that hard to keep these 5 little bits of information in your head. And now we can move on to something that's a little more challenging and a lot more fun, which would be, okay, so I thought I would clean up our diagram a little bit, get rid of the vertex information, the faces, the edges, the surface area formula, the volume formula. I'm going to replace that, you'll notice, with the Pythagorean theorem, the most famous geometry theorem of all. So we're going to end up using this to find the length of a line that travels from one vertex to the furthest away vertex in a cube. That's right. Remember, 2 times we'll be using the Pythagorean theorem. To help us figure out, let me put a question mark here. I think that's always a good idea, is when you're solving for something, let's put the question mark back. And start at the highest point. Start up here at A. And then I want you to travel straight down the edge of the cube. Go straight down the edge We're going to put this in a bright color. So you start up here and you come down. And then when you hit the vertex down below, I want you to travel all the way across to B, that other vertex. And you might not realize it at first, but that actually does create a right angle. When you're coming down the side of the cube and then you're cutting across the base of the cube, you have a 90-degree angle. And if you knew the lengths of these two purple legs, you would be able to find the hypotenuse AB, no trouble at all, because of the Pythagorean theorem. Well, the SAT is going to provide you with enough information to figure out the lengths of the sides of the cube. For example, they might tell you that the volume of this cube is 8. And they might make it seem scary by saying 8 centimeters cubed, but basically volume 8. And we already discussed the best volume formula is side raised to the third, and that is what is 8. So we put a cubic root sign around both sides of the equal sign, and we end up getting just the side is equal to the cubic root of 8, which is a very nice integer. It's 2. And I would then start labeling the sides of the cube. This is probably enough to label just 3 of the sides like this. So we know one of the legs of the purple right triangle, but we don't yet know this little leg down here until you see that there is another right triangle on the base of the cube. Do you see it here? Here's the right angle. And I'm going to change colors to something, again, that'll stand out. Let's get a different color going. We're going to notice that this leg, okay, and that leg, and here is the hypotenuse of that triangle on the base of the cube. And it's going to be super easy to figure out the length of the triangle on the base of the cube, its hypotenuse, the one down here. It's going to be super easy because it's an isosceles right triangle, which means this side and this side are the same length. Isosceles triangles have 2 legs that are identical, so they also have 2 angles that are identical, and it's a 45, 45, 90 right triangle. You may remember that the ratios of a 45, 45, 90 right triangle are already well known. The legs are both x, and the hypotenuse will be x root 2. So if we look again at our green triangle at the base of the cube, we already know that this is actually going to be 2 root 2 in length. We could get that by doing the Pythagorean theorem, but it's probably faster to remember the ratios of the isosceles right triangle. A little faster than doing the Pythagorean theorem. But guess what? Now we know the legs of the big vertical triangle. We know that the leg here coming down from A to the vertex below is 2 units. We know that this leg that's traveling over to B is 2 root 2. So let's plug that information into the Pythagorean theorem up here and see what we get. One leg is 2 units, so that's 2 squared. The other leg is a little more complicated, 2 root 2 squared, and it will equal the length of AB squared. So make sure we don't make any mistakes. That's 4. And it's really easy to make a mistake when you have something like 2 root 2 times itself, 2 root 2. Remember to multiply the 2 integers together. 2 times 2 is going to be 4. Root 2 times root 2 is root 4. But what's root 4 really? It's 2. So 4 times 2 gives us 8. So we're going to end up with 8 here when we square the quantity 2 root 2. And that will equal 4 plus 8 will equal AB squared. So this distance, where I have the question mark right here, is actually going to be root 12. Where did I get that from? Well, if AB squared is 12, I'll write it over here. If AB squared is 12. Then if I put a square root sign around both of these, I get the length of AB is root 12. So when you look down in the answers, you're going to notice there isn't a root 12. The SAT is going to simplify that radical. They're going to make it look like an integer and a smaller radical. So you have to remember how to do that. That's going to be our last step of the problem. Let me put it over here. Root 12 is actually the same thing as the square root of 4 times the square root of 3. If you multiply root 4 times root 3, you do get root 12. But root 4 is really 2. So you end up with a final answer of 2 root 3. This distance, all of AB, is 2 root 3. We've just found the length of the longest line segment that can run through the interior of a 2 by 2 by 2 cube. I'm going to make sure that you know how to do this. If you're taking lessons with me and you are on my weekly client list, then I will make sure that almost every lesson we practice this until I'm confident that you won't forget it. For those of you who are not currently taking lessons with me, please make sure you test yourself. I know that's hard to do, but I would give yourself a variety of cubes, a 4 by 4 by 4, a 10 by 10 by 10, and see if you can find the length of the line that would run through, the longest line that can run through the interior of the cube. I wish you a lot of luck in your SAT improvement, and this is Mark Schuyler. Until next time.